Okay, welcome back everybody. So today we're going to discuss the likelihood principle. You'll hear me talk about this periodically, whether or not I think it's important. It's kind of the philosophical thing that I think about the most in statistics. What I don't like about this is it usually makes statisticians fight whether or not you say you have to adhere to this principle. But saying that, this is commonly the thing that Bayesians will invoke to upset their frequentist peers. So, and I'll give you an example of that. I will point out there is no actual proof to this statement. So if you read through your book, they do have something that says proof. And I'll make the statement of the likelihood principle in a second. And then they say the proof has been pointed out to be incorrect. And so it's kind of fascinating. I've seen this go back and forth. And I read the literature, and this has been going back and forth since 1963. So Birnbaum produced the original proof. I'll say what the proof says. And it was pointed out that there's a flaw in that proof. Somebody came back and reproved it. And then a couple years later, somebody came back and said there's a flaw in that proof. And more recently, this has probably gone through 50 different iterations over the years. More recently, probably about 10 years ago, one of my colleagues, Deborah Mayo, who works over in the philosophy department, and to her credit, she studies the philosophy of statistics. So did you guys know that we have a department that studies philosophy of statistics? Most of the department is a philosophy of statistics department. So not philosophy of science, but specifically philosophy of statistics. And so this is always kind of fun when our department plays with their department. So, and we argue. So early in my career, Deborah came to me and invited me to her weekly dinners to discuss philosophical issues in statistics, and this issue came up predominantly. And we fought about it all the time. Nobody ever agreed. And so over lots of examples, and so I stopped going to the dinner because I felt that we're not being productive about this. Saying that, I'll try to lighten up this statement and basically say the likelihood principle seems to be a good idea. So whether or not you adhere to it all the time, you probably do not. So let's just write down the statement. The statement says this. Say there are two data sets differing data sets X. I'll just write down the data. The Xn, and there's another data set Y. And it doesn't have to be the same vector length. So I'll write it down in full-blown glory that there's two different data sets, and experimenter 1 sees this. And some other experimenter, we'll call him experimenter 2. Observes what? So they observe two different data sets. Experimenter 1 and experimenter 2 are both interested in the same problem, estimating theta. Okay, so in the common sort of notation, we might have some model, f of x, given theta. And the name of the game in inference is to take your x's and learn what theta is. So we start off the class talking about that. So to our visitors, this is our notation. I assume it's familiar. So this is the data, that's the parameter set, and there's an entanglement between those two things. So we don't get to observe theta, we get to observe x's, which are a proxy for thetas, and learning what thetas are. Experimenter 2 has a similar model, and they're going to try and learn theta as well. So theta has identical interpretations to both experimenters. They just observe two different data sets to try to do that. And we see this all the time. So different experimenters create different experiments, collect different data sets, and try to measure parameters. And so common setup. So these are the exact same two experimenters that we confronted back in when we were studying sufficiency. So we're back again. So we're going to see if experimenter 1 and experimenter 2 agree with each other. They typically do not. So So, but sometimes they should. So this is the likelihood principle. Likelihood principle says something about these two experimenters. And so I'll write it out the way that they write it out in the book. So if there exists a constant that depends on the data, x and y, but it does not depend on the parameter theta. Okay, so that's the important part. Such that, here's the key equation. It's a likelihood of theta given x is equal to this same constant times the likelihood function for theta given y. Then, experimenter 1 and 2 should have identical inferences about theta. So this is about what they write down. And then they go on to try to prove this statement. And they end up, here's the proof part of it. They end up saying that this is a direct result of the sufficiency principle that we've studied before, and what's called the conditionality principle. Meaning if you condition on your data and believe in the sufficiency principle, then you should have this result right here, that these two likelihood functions are proportional to each other, and you should get the same inferences. That's the part I don't want to discuss because there's no proof that says this is a direct result of the sufficiency principle and the conditionality principle. So it doesn't mean you have to believe this statement. Now I haven't explained this statement to you, what it actually means, and what it's implying, but there's no direct result that says if you follow the conditionality principle and the sufficiency principle, then you have to adhere to this. So I think everybody would agree the sufficiency principle is a good idea. So for those of you not in the know about the sufficiency principle, it says that you should use a sufficient statistic, i.e. a statistic that has all the information about theta. So for instance, in a normal model, if you're trying to estimate mu, and you know sigma squared, the sufficient statistic is x bar, or some of the xi's. And so it says you should build your estimator using that statistic. It doesn't tell you exactly how to build that estimator. It tells you you should use that statistic. That's what the sufficiency principle says. The conditionality principle says you should condition on your data in a formal probabilistic sense. So, and likelihood functions do that. So likelihood functions are functions over theta conditioned on the data. So you take your observed data, you plug it in, and you condition on it. So I want to point out that likelihood functions on their own, if I condition on the whole data set, I'm adhering to the sufficiency principle because the data is sufficient. And if I happen to encode it using the sufficient statistic, I will get exactly the same answers. So whether or not I use all the data or this compression that we've talked about for the last week or so. This also conditions on the data. So likelihood functions do that. So I will say that likelihood functions adhere to conditioning on the specific data set that you have, and it auto builds in the sufficient statistics. So it does it for you. So I would say if you believe in this, then you are following the conditionality principle. You're conditioning on the data. That's all the conditionality principle says. And the sufficiency principle, you should use the sufficient statistic. So I don't think it goes the other way around, but if you follow those two principles, you have to accept this. However, if you do except this, it goes the other way, that you have adhered to the conditionality principle, the sufficiency principle. Deborah Mayo came up with a proof that countered this. And she said, she's pretty bold about it. She said, I have proof that says that this is not true if you follow those two things. And I can prove that specifically. She has an error in her proof as well. So I tried to tell her. Other people have as well. So what happened? It wasn't productive. So anyway, I did go to a talk where she gave this lecture, and somebody asked a good clairvoyant question. They said, do Bayesians, and I'll say more about that in a moment, do Bayesians actually adhere to this always? And Deborah's answer is like they all claim to. And I chimed in. I said, I am a card-carrying Bayesian, and I don't. So no. So, and in fact, every Bayesian I know violates this principle. So I think most Bayesians will think about this because Bayesian posterior distributions condition on the data and condition on the sufficient statistics. So it's following conditionality principle and the sufficiency principle. So Bayesians do adhere to those two things, and what's happening in that, it's all about the likelihood function. So the likelihood function is the thing that invokes that. So the Bayesian might adhere to this principle. Okay, let's just look at what this says. All this says is that likelihood, and I should probably put an index on here and say this is the likelihood function for experimenter 1, and this is the likelihood function for experimenter 2. So there's no guarantee that they have exactly the same model. They don't put that notation in the book, so they just use likelihood function. So, but just keep in mind, these are presumably slightly different likelihood functions. I'm going to get rid of that notation. And just say that's implied by the fact that they're using different data sets. So I'll say the notation implies this, but it's not correct. So what this really says is that these two likelihood functions are proportional to each other. So likelihood of y is proportional to likelihood x, is all this says. So basically it's saying the shapes of the likelihoods are the same. And we've been talking about that for 2 months now. And that has information in it. So basically the wiggly shape of the likelihood function is telling you how likely certain values are. So this just says something like this. So I've got my likelihood functions. Experimenter 1's likelihood function maybe looks like this. In experimenter 2's likelihood function looks something like this. These are supposed to be raised to the same height, so that bandwidth is the same. So this is just a multiplicative difference. So I'm just multiplying one of these likelihoods and raising it up. But likelihoods are self-relative. So one of my pet peeves, it's not anymore, but back when I was in college and graduate school, if somebody used a mathematical term incorrectly, I would try to point it out to all my friends. And so that wasn't effective. So it just ruined the show. So for example, you're watching CSI or something like that, and they end up saying the likelihood that this guy is the criminal is 0.97. And I always say to my friends, or I used to, I would discourage you from doing it. That doesn't make any sense. So, because likelihoods on their own, they can be multiplied by any constant and still be the same likelihood function. So you can just scale those things up and down. They're not normalized like density functions are. And they're not probabilities. So if somebody says the likelihood is 0.97 and they don't give you another point on the curve, they didn't tell you anything important. So for instance, it's equivalent to saying the likelihood is like 4 million. Well, it doesn't mean anything. So, however, if I give you another point on the curve and I tell you its likelihood value, then you can say something about it. So for instance, let's just look at experiment number 1. So experimenter 1's likelihood curve, I guess we're looking at it, so I'll say it's this one right here. So that's experimenter 1, and this one's experimenter 2. So the top one, I just picked that arbitrarily. And so let's say experimenter 1 looks at these two values right here. So I'm going to call that theta 1, and I'm going to call this one theta 2. Okay, and let's say experimenter 1 finds, after they plug into the likelihood value, experimenter 1 says this. Their likelihood function for theta 1 I'm just going to change this and do this as 1 and this as 2. It doesn't matter. So I just want the notation to match up a little bit cleaner. So theta 1 given x is going to be equal to 3 times likelihood of theta 2. So theta 2 is smaller than theta 1, the likelihood of that value. How much smaller is it? 3 times. So what they would say. So what this says is the likelihood of theta 1 is 3 times higher than the likelihood of theta 2. Is 3 times greater. So what this says is that experimenter 1 might believe, so this is kind of an informal statement, theta 1 3 times more than theta 2. And that's what this statement says. So I have to multiply this by 3 over here to get that. And so what does that mean in terms of an inference? I'm not sure exactly what you're going to do with that, but one of the assumptions in this statement is that that is an inference to you, what these likelihoods are. What you do with it exactly, the likelihood principle doesn't tell you what to do. So this is a little bit of an overstatement. So it says they should have identical inferences, these two experimenters. If experimenter 1 believes this, and this is true, then experimenter 2 believes this. So experimenter 2 and I'll say if star is true, where this is star, this relationship. Experimenter 2 believes this is equal to 3 times the likelihood of theta 2. So you can just plug this in, plug in what experimenter 1 believes, take a ratio of everything, and this is an immediate consequence. So, and I'll let you put that together. So, again, there's this relationship between experimenter 1 and experimenter 2. This is what the relationship between theta 1 and theta 2 are for experimenter 1. But if you believe this, and I plug in this relationship, and I replace what experimenter 1 believes in terms of experimenter 2, they will have the same inferences in terms of their likelihoods. And so that's what this statement is saying. Again, this should have the same inferences. It's all about what are you going to do with this likelihood function at the end of the day. And the likelihood principle does not address that. So it doesn't tell you what to do. So that they should have the same inferences implies that they're going to do the same inferential sort of procedure using the likelihood function somehow. So for instance, for a Bayesian, the assumption is that they're going to pick the same prior. They're learning the same theta, so they should have the same prior beliefs. So there's an overarching assumption for Bayesians saying that their paradigm for picking priors is identical as well. And the likelihood principle doesn't say that. So your priors shouldn't be dictated just by the likelihood function. Saying that the likelihood function is going to express the nature of that parameter, and it probably has something to do with why you pick priors. So again, I looked at this for a long time, and I thought, does this mean that we have to adhere to the same principles on picking priors? And it doesn't say that. But there's this strong implication that I would say ardent rapid Bayesians are making that say, yeah, well, we're going to assume, of course, that's obvious. So again, this is one of the things people fight about. I will say something. Sometimes Bayesians violate the likelihood principle when they pick priors. And I would say almost always they do that. So Bayesians oftentimes are violating the likelihood principle just off the bat. There's something else that they'll do. Is in this class, I can write down the data came from a certain generating function that has a particular likelihood function. So in this class, I'm always writing this sort of stuff down, that we get to assume maybe the xi's are coming from some model, and we know that model. And so in the real world, everybody that's ever come to me with a statistical question never had a model in hand. So here's the data, oh, and here's the generating function. If they did that, if they had it, they wouldn't need me. So what do I usually do? I usually look at the data for a very long time. I build models. I look at residuals from those models, and I adjust my model. That is a violation of the likelihood principle. So to construct the likelihood in the first place. So again, there's no probability models over probability models. So we pick them for particular reasons. So the likelihood function is or the likelihood principle is a fiction from the get-go, because usually you're going to violate the likelihood principle in constructing your likelihood. So this is a philosophical mind game that people are playing. So assuming we all agree on the model and we agree on that, then maybe we should come up with the same inferences. So let's imagine our two experimenters. So let me give you an example of this and what can go wrong if you don't adhere to the likelihood principle. And I think this is probably the strongest argument for the likelihood principle, is what goes wrong if you don't adhere to it. And this is the sort of thing I want you guys to think about. So if you violate one of these principles, what could go wrong in that situation? And if something goes wrong, if you recognize that, you need to address it. So, okay, so imagine our two experimenters. So they're doing science, collecting data, and they make some discoveries. So they're walking down the road, and experimenter one sees this data set. Cool, this data set. So experimenter two walks down the road, and he sees this data set too. Ooh, this data set. I'm going to try to infer theta. In our case, theta is this p. So this is the model parameter. Now, experimenter one, in terms of our fictional mind game that we're playing, this is usually what I call theta. So experimenter one and experimenter two are both graced with a little bit of knowledge. They're both graced with this generating function. They both agree that this is responsible for this data being generated, i.e. it's a Bernoulli model. So this is just Bernoulli. One of my favorite distributions, because I can explain so many things with it. So they both agree with this. Why do they agree? Because this is a fiction and I said so. So they both believe that this data was generated as a Bernoulli coin flip. So it seems like they have the same knowledge about the data. But experimenter one believes something slightly different than experimenter two. So let me be explicit and write this down. Experimenter one believes n equals 10, these are the number of trials, was fixed in advance. So this is an observational study. They didn't construct the data, they didn't do a design experiment and say how the data was collected, and they didn't go out and collect it explicitly themselves, so they don't know exactly. All they did is walk down the street and find this vector of data. And it's like, I wonder what P is. And that's their question. You know, I've got this vector, I agree that it's Bernoulli, so there's a number of assumptions that everybody agrees on. It's Bernoulli, everything is IID, so everything is exchangeable, maybe. But experimenter 2 doesn't believe that. So experimenter 2 believes in this mechanism that everything is just an IID coin flip, but experimenter 2 makes this observation that the last draw is a head. And so experimenter 2 makes another arbitrary assumption. So experimenter 2 believes the data was generated until they observed the fifth head. And this is an arbitrary assumption. So, i.e. there's 5 heads right here. Experimenter 2 believes that that wasn't random, that there was a stopping rule for collecting this data, and there is some stopping rule. So we agree on the mechanisms, the model relationships between the heads and the tails and the P's, but they disagree on the stopping rule itself. What made this data stop growing? So experimenter 1 seems to make an arbitrary assumption. This data was going to be generated until there were 10 coin flips. Experimenter 2 believes the data was generated until there were 5 successes. So I'll call my successes my heads. So 5 inches. I would agree those are just perfectly reasonable assumptions. I have no idea what generated this data. Both seem to be reasonable assumptions. You've got to assume something about it. The question is does it matter? So, and we're going to find out we could. So, and what we'd like in statistics is all these arbitrary things that we don't know shouldn't confound our inference. So, let's just talk about this a little bit. I think this is the easier case that most people are familiar with. So in the Stat 101 class, you've played with that assumption lots of time, and it's 10. So somebody probably should have asked, why do we know that it's 10? So how did you know that in the first place? So, and your professor would say, it doesn't matter. And you're like, well, if you believe in the likelihood principle, it does. So, well, if you, I should rephrase that. If you believe in the likelihood principle, then it might not matter. But if you don't believe in the likelihood principle, it could matter. And so your professor would kick you out of class at that point. So stop hassling. So it's a fun thing to do. So you can antagonize people with the likelihood principle. Okay. Who thinks this assumption is more reasonable than that assumption? Who thinks that assumption is more reasonable? They're equally as reasonable. You have no idea. So you're probably more familiar with this. So that might seem more reasonable to you because you're acquainted with it. There's a big difference, though. Just because you're acquainted and you're familiar with something doesn't necessarily make it more reasonable. You just like it because you have affinity for it because you're familiar. So, what distribution is experimenter 1 invoking? Binomial. So the experimenter 1 believes the data is binomial. So this is binomial. So, what's random for experimenter 1? And it's fixed. Yeah, the probability of the successes. You could arbitrarily say the number of successes. So, or you can say, or the number of failures. It's the complement, if you know enough from it. So, number of successes were random. And so experimenter 1 believes that the model so I'll just write it down, looks like this. So I'll say 10 choose x, p to the x, 1 minus p to the n minus x. So that's a binomial distribution. I trust this is familiar, guys? So stat 101. So everybody knows this. That's a binomial distribution. And you could prove that. You could explain where that normalizing constant is. It's just the number of ways I can rearrange everything in here, and it doesn't change the number of successes or failures. So it's just the number of rearrangements. So I'll just give you a prelude. Let's imagine experimenter 1 and experimenter 2 do not adhere to the likelihood principle, and eventually we're going to do a hypothesis test conditioning on P naught. So this is the whole P value war that we're going to talk about in a second. And this is the thing that Bayesians would use to antagonize P values. I don't want to give them a name yet because there's different types of P values, how they compute their P values, what they do with them, so on and so forth. I don't want to call them frequentist or classicist yet. I just want to say this thing, P value. So they're going to base their P values off of this model. So experiment 2, two's model is a little bit different. Say experimenter 1 has binomial representation. Experimenter 2 has something, it's not binomial. Who knows what it is? It's negative binomial. So question, what's random in a negative binomial distribution? Yeah, it could be the number of trials. Anybody else have an answer? The book will encode this 2 different ways.
The number of failures.
Yeah, exactly. So there's 2 different representations to the negative binomial, and one is just a shift of the other. And so be careful, it does change the representation of the normalizing constant. In my experience, it usually makes first-year graduate students confused when they glance at it for the first time. Where did that everything come from? How do I remember this? Because it changes all the formulas. So if the number of failures is random and the number of successes is fixed, then the total number of trials is just those successes added to the failures. And so it's just a shifted representation. Let me tell you how you can remember. So does anybody know what the representation is if I end up saying the number of failures is random? You want to take a stab? We'll call our number of failures x as well.
X plus I minus 1.
X plus
R minus 1.
r, so that's the number of successes?
Yeah, so far.
Or the number of failures, or successes minus 1?
Okay.
Minus 1.
And then you choose the number of failures.
It doesn't really, it could be the number of failures,
Or it should be successes.
or it could be this one.
Yeah.
It doesn't matter. So if I put this down here, or I put that down there, they're the exact same thing. So I'm going to just write down x. Actually, let's just make it easy. I'll make it successes minus 1.
Okay. And then P raised to the number of successes we see, and 1 minus P raised to the number of failures.
Then 1 minus p times the number of failures. X. That's it. So good job. Nicely done. Most people don't get that so quickly. Let me show you how I remember this. So, because I had a hard time remembering and I get confused. And on a test, as soon as I get nervous and confused, I start making errors. So, let's just have a glance at this data. So I'm going to write out these 10 positions, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And experimenter 2 believes this was a hit right here. That wasn't random. That's the stopping rule. So again, we've got to be careful about these things. They could affect your inferences. So what's the probability that that happened? P. So we know that. So, and all I know about this stuff right here, what experimenter 2 is saying, is this thing right here has 4 successes and 5 failures. And this happened in 9 trials. I'll get rid of this. We'll just remember that there's 4 successes in there and 5 failures. And it happened in 9 trials. And so that's the random bit for experimenter 2. Question is what's the probability that this happened right here? So I'll just say, we know what this is. This is going to be 9, choose 4, times P to the number of successes. There's 4 successes in here. And there's 5 failures. So I don't care which order these happen in. So that's the idea. And so what I did is I just kind of invoked my knowledge about binomial distributions to come up with that. So again, this thing was fixed. And then once I multiply by this P, I have that right here. So this is the first part, and this is the second part right here. So that's the probability distribution that experimenter 2 is adhering to. So remember the negative binomial distribution, I always just draw this picture. I anchor that, I put P here, and then I just think binomially about the rest. And I can think about that all kinds of different ways, and I can never forget that once I draw this picture. And think about it this way. So doing this, I never get confused. So this P gets absorbed right there, and so this thing is 9 choose 4, P to the 5, 1 minus P to the 5. Let's write this out notationally. It looks like that, right here. Where this thing, right here is a 4, 5 minus 1, and this is a 4, 5 minus 1. And X is the random bit, the number of failures. So that's there. And this right here is going to be the number of successes. So that's a 5. So for this problem that experimenter 2 is studying, they're going to base their inferences off of this distribution, and the 5 right here was fixed. So that thing is fixed. And experimenter 2 believes something slightly different. They believe this bit, this is a 10 right here. So this is fixed. It almost seems like it shouldn't matter. So, but it can. So they have 2 different generating functions. And these generating functions right here, so I'll just write in what they believe that this right here is 10. They're going to plug that in. But for their particular data set, both of them have the same function right here. So for this particular data set, this is going to look like P to the 5, 1 minus P to the 5. If I plugged everything in for that particular data set. And this right here, for this particular data set, for experimenter 2, they also see this kernel of the distribution is P to the 5 times 1 minus P 2 to the 5. So the point is, in this example, and I do think this is the most compelling example of fourth likelihood principle, we don't need proofs, we just need examples. That their likelihood functions are the same. That's the whole key point right here. And so they should come up with the same inferences. Let's assume that experimenter 2 and experimenter 1 are going to do a classical hypothesis test. And let's see what happens. This is my least favorite thing in all of statistics when people do this. So forgive me for it, I'm just making a point. So, some people have tried to indoctrinate me with this idea, and you better accept this. So I think all through my undergrad they did this to me. So they write something like this down. H naught is P is equal to P naught, something like that. And they're going to test this hypothesis. This is called the Null Hypothesis. And everybody has seen this before. So everybody who's ever taken any statistics class has been introduced to this idea of testing this hypothesis. I really wish we didn't do that. If there's one thing I could do in all of statistics is to, not for the first time you take a stats class, that you start addressing this question right here. So let's just talk about it for a second, and then we'll carry on. Why? I'll just give you my opinion. The reason I don't like this is because I already know the answer to this question. So the question is P equal to P naught? And so I know it's not. So why?
You don't know it exactly.
Yeah, it's a continuum. So P lives between 0 and 1. P lives in that continuum. And the probability that I pick the right true value is infinitely small compared to all its competitors. So there's no way I pick the right thing. So let's think about a coin flip. It's very common to ask the question, is the coin fair? Is P equal to 0.5? I already know the answer. It's not. So definitely no matter what you pick, it's not. And it turns out most fair coins that you flip, the tail, it has higher probability. So it's 52 to 48. So I've seen lots of experiments where people have convinced me of that question. Percy Diaconis, genius probabilist, is an expert on this problem, and he's flipped coins millions of times to demonstrate. So it turns out it's true. People have actually done it and seen what humans do. Now I do know people that can flip a coin and bias it just by the way they catch it. So I have a friend that's incredibly good, 9 times out of 10, he can flip a head from a quarter. So, and I thought that was remarkable. I sat around, I tried to do it for an afternoon, and I was like hitting 7 pretty quickly. 7, 8, so I could bias it as well. And so just get used to like how you're holding it, flip it, and catching it right now. So you can train yourself to do that. It's all about the height at which you catch it and how much spin you put on it. So what Percy actually does is he says it's so biased that anybody can do that as well, and everybody biases the coin when they flip it, so he spins the coins. And it turns out that's much more random. All things you can think about. You can try it out. So if you're like me in grad school, you'll be up in your office for the next hour flipping coins. So, okay, maybe don't. So the reason I don't like this is because why guess it's something that I know is not true? Why don't we just estimate P? So what I like people to do, I wish what we did in Stat 101 classes is get them to just draw a likelihood function and think about it a lot. So what does it mean? And then we can give them formal analyses for dealing with these things. But this is a typical thing. So this is the smear that Bayesians invoke to antagonize their Navier-Pearsonian friends. So I'll say P is greater than P naught. So this is a one-sided hypothesis test. And I'm using a one-sided case so that I'm not invoking all kinds of issues that happen in the sharp test, which we'll talk about in about a month's time. So this doesn't have all the issues that I'll really beat up once we get into chapter 8. So experimenter 1 is going to base his p-value, so experiment 1, p-val would look like this. Sum, and they're going to end up plugging in the null hypothesis into their distribution. So they're going to have 10, choose x, p naught raised to the x, 1 minus p naught raised to the 10 minus x. So what a p-value does is they sum over more extreme data. We're going to talk about the ramifications of this once we get into chapter 8. So I'm assuming you guys have done this before. So when I was in Stat 101 or some version of that, this is about all they have us do. So over and over again, state the null hypothesis, compute the test statistic, compute the p-value, and make a conclusion. They're turning you into a robot. So when you do that, you're following this procedure. And so I personally don't love that. Okay, question is what should I sum over? X has to do something. So for this hypothesis test, what should my bounds be? The whole contradiction thing, think about tail probabilities. So here's the correct tail direction. This is 5 or more successes. So this is the probability of 5 or more successes. So this might seem a little awkward. And if it doesn't seem awkward to you, you've been indoctrinated. So this is your p-value. So p-value is the probability of more extreme data than you've observed, including that data conditioned on the null hypothesis. And so the idea is that this is a proxy for deciding for or against this decision. I do understand most people say you can't accept, you just fail to reject. Let's get rid of that language. At the end of the day, you're going to do something. So I'm going to say you accept the decision. So I get it, if you go back to Popper, that you can't really accept anything, you can just falsify. So it goes back to falsification, which is the general scientific method. So again, all indoctrination. So good logic, it's true. This isn't exactly that, but it's based off of that idea. So that's their p-value. Experimenter 2 is going to compute a different p-value. I'll just write this down real quick. Experimenter 2's p-value is going to be something similar. So, and I'm going to base it off of this thing that we wrote down before. P naught, this is going to look like a 5. That's fixed right there. And this is going to be 1 minus P naught to the x. The question is which tail direction do you sum over? In this case, the failures are random, so I'm thinking about this in terms of the failures. That's the way we've encoded it. So x is going to go from 0 to 5. So this is 5 or less failures. I'll let you work through that logic. My job right now is not to train you on doing classical hypothesis testing. So you can go home and think about this tail direction, and see if I've computed the right tail directions. This is correct. So failures are the things that we're going to sum over, so that's its tail probability. The point is that these numbers are different. I'm sure I could find a P naught for this where they're the same, but in general, they're going to be different. And I could have picked a P naught for this problem where this is going to be over 0.05 and this might be under 0.05. So there'd be some P naught I can do that with, and then we can have some great debate as to whether or not we reject everything, but I don't want to indoctrinate you any further. The key point is that these are different. And so potentially, experimenter 1 and experimenter 2 are going to have two different inferences. What has gone wrong? We summed over tail directions of the probability distribution, and we did not use the likelihood function. So the likelihood function is a function of the p's. Next time we'll come back and I'll say what a Bayesian might do, or something like that, and I'll just say the likelihoods are the same, and so maybe you should come up with the same inferences. But if you do this, this is a clear violation of the likelihood principle, and it's an example of when you assume something arbitrary like the stopping rule, it could infect your inferences. So I'd say if you do adhere to the likelihood principle, this won't be an issue for you. Let's come back next time, have a little bit more discussion about it, but then we're going to jump into chapter 7. So I'll release a few more homework problems for you today. You have your simulation assignment, so keep working on that. Try to give you a couple days of break so you can think about one thing, but the new homework's coming out. And then we're going to turn the chapter and move to chapter 7, stuff that's a little bit more practical, and I'll say how do you utilize these different principles. That's it for now, guys. Have a great weekend. Just hang tight.